Hi, it's Dr. Weideman again, and I'm going to show you how to use StatCrunch to work some problems from Chapter 5 in our textbook. So in the ebook, in my Stat Lab, I've pulled up Chapter 5, and I'm going to look at this problem here about car speeds. And it tells us that John Beal of Stanford, California, recorded the speeds of cars driving past his house, where the speed limit was 20 miles per hour. He had 100 readings, and he got an average or a mean of 23.84 with a standard deviation of 3.56. The first question is, how many standard deviations from the mean would a car going under the speed limit be? Okay, to do this one, I just need a calculator, and I'm actually just going to do a z-score, because that's all a z-score is. So I'm going to take the car going under the speed limit, which would be going 20 miles per hour. I'm going to subtract the observed mean, which was 23.84, and then I'm going to divide by the standard deviation, which was 3.56. So a car going the speed limit would be about 1.08 standard deviations below the mean. What would be more unusual, a car traveling 34 miles per hour or one going 10 miles per hour? Alright, so let's go ahead, and we could do z-scores for these, but I'm also going to show you how to use some tools in StatCrunch that are helpful for problems like this. So we're going to go ahead and go into StatCrunch, and I've already got this data set pulled up, but right now what we're going to be doing is using tools called normal calculators, and there's a whole series of calculators in StatCrunch. We're going to use the normal calculator. And the thing that you need to enter in first is the mean, which was given as 23.84, and the standard deviation was reported to us as 3.56. And we want to know what was more unusual, a car going less than 10 miles per hour. So let's go ahead and compute that. So a car going less than 10 miles per hour would be going, the likelihood of that happening is really, really small. So it's 0.000, 4 zeros and then a 5. And then how about going greater than 34 miles per hour? Okay, and this probability here is larger. So the more unusual one would be the car going 10 miles per hour. And we could go ahead and calculate the z-scores. Let's do that. So 10 miles per hour, we take 10 minus the observed mean, remember, which we have in our tool there, 3.84, and then divide by 3.56. So that car going 10 miles per hour is 3.89 standard deviations below the mean. Okay, and then the car going 34 miles per hour is, and I'm doing the same calculation here, figuring out the z-score, how many standard deviations, so it's 2.85. So we see that the car going 10 miles per hour would be more unusual. Okay, let's go back to the ebook, and if I can get over there, I seem to have lost my ebook here. Alright, let me pull it up again. I'm not sure what happened to my book. Alright, so let's go back to Chapter 5. I've lost where we were working, so let's go back in, and we're on page, so that was the problem 26 on page 135 rather. And so now I'm going to go over to the next page from that, 136, and there's a continuation of that problem, so 136. And it's using the same information that we just had, and it's problem number 38. It's at the bottom of this page here. And I'm going to show you how to use some tools in here. So for the car speed data in the exercise 26 that we just worked on, they want to know whether it's appropriate to apply a normal model. So I'm going to show you how to do those particular figures right here in StatCrunch. So go ahead and go to Graph. And how I got to this data set also is I went to StatCrunch textbook data sets, Chapter 5, and this is the car speeds problem. You could also click on it from the e-text. On the prior problem there was a little link there to get to the data set. So I'm going to go to Graph. First thing I'm going to do is a histogram. Let's take a look at the histogram for this data and see how it looks. And it looks really nicely unimodal and fairly symmetric, so it looks like we could assume an underlying normality there. We could also do a box plot, and I want to make sure on box plot, remember when we did box plots, we're always going to use the fences to identify the outlier, so let's take a look at that. There actually is one outlier here, but it still looks fairly symmetric. And then the last thing we could do is the probability plot, which StatCrunch calls a QQ plot. and select speed and compute. And if you remember from the handout for this chapter, we're looking for a straight line here. We want to see the data points here, graph following a fairly straight line, and that looks pretty good. So I think we could assume underlying normality there. And then the last problem I wanted to do was on the next page, and it's problem number 48. And this is about a tire manufacturer who believes that the tread life of the snow tires can be described by a normal model with a mean of 32,000. I'm going to go ahead and go back here and get my normal calculator up because we're going to use that again. And the mean given was 32,000 miles for these tires, and the standard deviation is 2,500. Okay, so we're going to use that. And let's see what questions they're asking. If you buy one of these tires, would it be reasonable for you to hope that it would last 40,000 miles? Okay, so let's get back to our tool. And that would mean we want to know the probability that our tire lasts more than 40,000 miles. And so that probability is pretty small, 0.0007, so much less than 1%. So that's pretty unusual that our tires with this particular mean lifespan would be expected to last 40,000 miles. Approximately what fraction of tires can be expected to last less than 30,000? Okay, so now we want to go less than, and we want to put in here 30,000. And so about 21%, 21.2% of tires are going to wear out 30,000 miles or less. Approximately what fraction can be expected to last between 30,000 and 35,000? Okay, so now you're going to switch on the tool here to the between tool. And now you want to go between, and it asks us between 30,000 and 35,000. And so the tool is going to compute the area between those two numbers. And so about 67.3% of tires are going to last between 30 and 35,000. And the next question they ask you is an interesting question. They want you to estimate the IQR of the tread lives for the tires. All right, so now what we want to do is we want to find the area between here. We actually want this area to be 50%. So I'm going to go ahead and put that in there. And it's not going to help me there. So what I'm going to do is go back over here on the standard one, and let's go ahead and find the lower 25% because that will tell us. So here's Q1. It's basically 30,314. Okay, and then Q3 is going to be on this side up here, so we want to go greater than, and we want this here to be 0.25. Okay, so that's how you would compute your two Q1 and Q3 and get the IQR. So let me just jot down these numbers, and then I want to go over to the other tool to show you how that jives. And let's go back here and do the 0.25. I just want to show you something else with the tool, the other tool, and it was 30,313.8. So if I go to the between here and I put in those two numbers I just calculated, 30,313.8 was the lower bound, and the upper bound is 33,686.2, and compute. And so I've gotten that 50% between, which is what I expected. And actually the IQR, remember, is going to be, let's pull our little calculator up again, it's going to actually be the difference between, so 33,686.2 minus Q1 30313.8 equals, so about 3372 is the IQR. And let's see, I think there was one or two other questions. In planning a marketing strategy, a local tire dealer wants to offer a refund to any customer whose tires fail to last a certain number of miles. However, he doesn't want to take it too big of a risk. If the dealer is willing to give refunds to no more than 1 of every 25, for what mileage should he guarantee those tires to last? Okay, so 1 out of 25, let's go ahead and divide that, and you might know that's going to be 0.04. So I want to go back to my tool, and I want, let's get back to the standard tool here, I want to find the greater than, no, I think I wanted greater than, and let's put the 04 over here. So he wants to figure out where he's going to make that adjustment, and so let's go back and look at the wording of his question. For what mileage should he guarantee the tires to last? So if he guarantees the tires to last for say 36,000, 36,400, then he's only going to have about 4% of the people come back later and say, my tires didn't last long enough, and he would have to give a refund. So I hope this will help you working with our different tools that are available in the StatCrunch package.